Continue our discussion of machine learning with discussion of AGN identification.
Yeah, I'm sorry for the switch of title. So hi, I'm Kurt. I'm a 6-year PhD student at the University of Kansas, where I work with Allison Kirkpatrick. I'll be talking to you today about AGN Boost. This is a machine learning approach I've sort of made to try to identify AGN and try to estimate photometric redshifts from just near-cam and Miri photometries and colors. So I'm going to start with a claim that I hope is not too controversial, in that just finding AGN photometrically is a very hard task. You of course look at, so you have a template here of an AGN and star from galaxies. They look very different. You might think that this should be very easy, but what we find is that this is not at all the case, right? So there are sort of two what we have found to be notable obstacles towards doing this with JWST Miri photometry and colors alone. The first obstacle is that when you use just a few closely spaced photometric points, it's quite easy for star-forming galaxies to sort of mimic an AGN power law. And the second point, which is admittedly related to the first, is that inactive galaxies, so galaxies that are weak in the mid-infrared, either due to low metallicities leading to weak pH features or just low intrinsic dust masses, these inactive galaxies can also mimic an AGN power law. So I have here a quick, probably the simplest video you've seen all week, just showing you 4 different templates here. So we have an AGN in red. We have a composite galaxy. So this is a 50% AGN emission, 50% star-forming emission. We have a star-forming galaxy, and then M82 here is sort of proxy as sort of a mid-infrared weak galaxy. So what we're going to do is see how, as we redshift these templates in our Miri photometric bands, how the color spaces of these things change. What we really just sort of see is that depending on the redshift, there's just a lot of degeneracy within this color space. Really can't confidently make any claims for really anything except the AGN, which, right, in reality, we don't really see many things that are, where 100% of our infrared emissions come from AGN. So the red point's a bit idealized. But when it comes to star-forming galaxies and composites and weak, mid-infrared weak galaxies, it's really hard to make any confident claims about our capabilities to identify these things. So we really need, clearly, some kind of improved methodology to really solve this issue. So in a very simple view, right, you can just imagine taking whatever observables you have. So we have, photometry and derived colors and any other derived quantities you might be interested in. You can feed these into any machine learning model of your choice, of course, and try to estimate things like the AGN fraction. So this is a fraction of mid-infrared light that is attributable to an AGN power law. We'll be seeing this again, and also things like redshift and star formation rate, anything that you're really interested in. And this is where AGN Boost comes into play. So this is a machine learning framework I've built. This is based off the XG Boost LSS algorithm. If you're not familiar, you might be familiar with random forest algorithms, where you build a forest of decision trees in parallel. Extreme gradient boosting kind of takes a different approach, where you instead build decision trees in series, where each subsequent decision tree sort of learns off of the mistakes of the previous ones. So XGBoost LSS is able to sort of, rather than make point prediction estimates of parameters, estimate the entire conditional distribution of them. So where it's trained on data that I'll get into on the next slide, but using 7 near-cam, 4 Miri bands, 55 derived colors from those, and also the squares of those 55 colors to estimate 2 things. So again, the AGN fraction and the photometric redshift. And the kind of goal here is to provide a computational fast method to sort of supplant color selection to try to quickly and easily find maybe subpopulations of candidate AGNs to investigate further. Briefly here, AGN Boost is trained on mock galaxies from Seagal, which, if you're not familiar, is a sort of grid-based SED fitting code that you can essentially just run in reverse to create mock galaxies. So we create a catalog that's rather comprehensive of about 10 to the 9 galaxies that we then uniformly downsample to about 10 to the 6, so that I can effectively train this on my personal computer. We split this set of a million galaxies into training, test, and validation sets, and we do some rather comprehensive hyperparameter tuning because XGBoost has a plethora of hyperparameters. And then we, of course, test it on the set aside, and then also on real observations from the mega survey that I'll touch on in a little bit. I will note quickly, we do spend a lot of time sort of validating that these mock galaxies are representative of what we see in real observations. I really can't go into detail about this, but this is just a color plot showing the red lines are sort of the contour regions of the Seagal mock galaxies, and the stars and black points, which you really can't see, are the actual galaxies. But please feel free to ask me about this. So then we look at the performance of AGN Boost now on the set of test galaxies. We have on the left for the FRAC AGN parameter, we are seeing on the y-axis the expectation value of the FRAC AGN parameter for each individual galaxy compared to its true value. On the right for redshift, we see really the same thing for both of these. The white dots show you the median in each bin. Your whiskers show you your extrema. The blue region is a 2 sigma region. We see consistent good performance across all ranges of values, both for the median in terms of the outlier spread. But this is sort of an idealized case. These Seagal galaxies, unfortunately, don't really factor in any sort of photometric uncertainty into them. It is difficult to sort of ad hoc put them in. But what I've done is sort of gone through and sampled from our real JWST observations. You can build correlations between the photometry and its uncertainty and sort of sample out what might be sort of naive, realistic uncertainties and redo this process. We're looking at this left side first. You see that the median points are still on our 1-to-1 relation, but what we do see, of course, is that the spread has increased dramatically. But we do still only have a 15% outlier fraction of 11%. So we're still relatively centered on our 1-to-1 relation. Now, the redshift one's a bit more interesting. Of course, you see at low redshift, you see a similar thing as we do for the AGN fraction, but above redshifts of 3, our medians are now well below the 1-to-1 relation, and our outlier fractions increase dramatically. So this might perhaps not be a great approach to take for high Z photometric redshifts. So now when it comes to looking at real data, we're losing data from the mega survey. This is Alison Kirkpatrick's sort of pet MIRI extension to NIRCam Sears observations. So we have in total about 2,000 galaxies now with MIRI and Sears NIRCam, and about 700 that are missing no photometric bands between NIRCam and Sears, and we have some pretty strong signal to noise constraints on the MIRI band, just because we found that if you don't impose those constraints, you really gain no information by including your MIRI bands, because there's so much degeneracy there. So now we're going to look on the right side first. So we're looking at the photometric redshifts from AGN Boost compared to the spectroscopic redshifts that exist for any of those galaxies. We see this is quite good, considering that we're only using near-infrared and mid-infrared photometry. We see below redshifts of 2, it's quite good, I would say. Above redshifts of 2, you can imagine sort of the pH features are now sort of redshifting out of the MIRI coverage, so we do see a noticeable drop in performance. And we can also compare to photometric redshifts from Sears that I should note were derived from HST and NIRCam photometries with easy fitting, so they don't go out to quite as long redshift as we do, but they of course trace the Balmer break a lot sooner. We see a similar trend that below redshifts of 2, it's relatively good, and above that, the predicted performance of AGN Boost seems to drop. I want to just quickly highlight these 3 little extreme outliers here on the right side. I will note that these 3 galaxies also have photometric redshifts from Sears that are sort of in line with the AGN Boost estimates. Their P of Z distributions show no high redshift peaks, but looking at the SCDs of them, they exhibit very weak bomber breaks. So you can imagine why you, of course, might not be able to confidently derive photometric redshifts. So now to compare to get some sense of frac AGN performance from AGN boost, we of course need something to compare to. There aren't literature values of this, so we have now gone through in our set of like 700 megagalaxies, ran them through Seagal with the same parameter space, using of course the known redshift for each galaxy. There's about 250 of these that have what we would consider good fits from Seagal. So it's about 40% of the sample. And you're now seeing, y-axis from AGN boost compared to the Bayesian AGN fraction from Seagal. There's a lot going on here. Ignoring the colored points for now, just kind of looking at the white median points. You see relatively good agreement. I would say, you could say that about there's 173 galaxies, about 70% of the things on this plot with AGN fractions below 0.3 for both Seagal and AGN boost. I've colored both blue squares and purple stars. These are sort of what we might consider like our extreme outliers. So in terms of their AGN classification, so things that are below the AGN threshold in AGN boost, but above it in Seagal and vice versa. Looking at the SEDs of these and then sort of refitting them with Seagal, forcing more of the estimate from AGN boost. I've sort of found that the Seagal fits really aren't quite reliable, and that it does seem that the values from AGN boost are more likely. Happy to talk about them more later. So now if we look at the whole sample of megagalaxies, we find about 83 AGN candidates. I use the word candidates because we're of course not super confident about these. We can now make a plot here showing you the number fraction of AGN in different redshift bins. The numbers above each point just show you the total number of galaxies in that bin. Notably, AGN boost seems to find a very large, excessively large fraction of high redshift AGN. This, of course, needs further follow-up. I'm not particularly confident about this. So I'm currently trying to look at the X-ray we have to try to constrain whether or not how many of these actually are AGN, but at the very least we now have a much smaller sample that we can follow up in future proposals. I'll very briefly here just talk about another thing that we've built into AGN boost, which is photometry imputation. So a big problem, of course, is you're oftentimes missing photometries in various bands, which can be a big problem for models that might not work with that. So there's this thing called the AGN algorithm, which is just it's a generative adversarial network. You have a generator and a discriminator that fight back and forth, trying to improve their performance of making fake data, testing how good it is, and so on and so forth. So you can use this to sort of statistically replace missing photometric values. So I've done this here. The top row is showing you where I've gone through and made one myriad band randomly missing. The second row, two bands in randomly missing, and then three myriad bands randomly missing. You run it through the network sort of 100 times to get some estimate of uncertainty on the imputed value, and you can sort of try to recover or replace the values, and it seems to work relatively well. And then feeding these back through AGN boost to, of course, now see, well, how do these imputed values change the estimates from AGN boost. So in the top, I've ran the imputation algorithm. On the bottom, I have just left the values missing. XGBoost does allow you to run with missing values through a sparsity-aware split finding algorithm. But what we see is that when we leave the values missing, so on the bottom, the performance is notably poor. Whereas if we recover the values, especially when there's just one or maybe even two values missing, we're able to recover them relatively well. So I'll conclude there. There's two QR codes here. The left one will take you to the AGN Boost GitHub. There's rather extensive documentation, so feel free to try and use it for anything you can imagine. And the right takes you to the paper that's now in the archive.
Thank you. All right, why don't we get our next speaker setting up? Yeah, why don't you plug in, and then while you're plugging in, we can take a question.
Thanks. So I have a question about the training set.
Sure.
So I think currently you're generating your training set using the Seagull SCD
Yes.
fitting code. So I was wondering, because in general, there's more than Seagull that is being used in like SED fitting for composite galaxies, like containing galaxy and AGN components. And I was wondering if there's any like plan in future to generate training sets using other codes as well, and see if there's going to be any domain shift between, from Seagull to any other SED fitting models.
Yeah, it's a great question. I don't have any plans right now. I'd love to do that, though. I think it's a great point. It'd be awesome maybe to even pull in from, mock images of galaxies from simulations to maybe, pull in actual, uncertainties and things. But it's definitely something that should be looked at.